Hey everyone. Actually, Andreas made this quite nice presentation about real-time hybrid shaking table theory developments and applications. So my title is Other Developments and Applications. And I'll basically talk about two things. First is the analytical investigation of the effect of time delay on real-time hybrid simulation and some implementation of time delay in OpenSees. And the second one will be related to the implementation of the three-variable control in our controller here for improving real-time hybrid simulation shaking table testing. So I'll start with the first one. So I've shown this yesterday, the conceptual investigation of the effect of time delay on hybrid simulation and how it corresponds to increased or positive or negative damping, and we had a lot of talks today about this. And also I've shown this also yesterday, the experimental investigation, where we have really observed that time delay results in negative damping, and that would lead to increased response, and it could even lead to instability. So what I'll show now today is the analytical investigation. So basically here what we are trying to do is we are trying to simulate real-time hybrid simulation with errors fully in the analytical domain. So let's say if you are representing your experimental substructure with a corresponding analytical part, and then you still have two substructures. So we'll try to simulate this setting with errors in the simulation. And to do that, basically, we need to define the error. And we define the error as velocity times the delay, because error is proportional to velocity and it's proportional to the delay. So this is my error term, and this is the computed displacement, and what I call is here is the realized displacement. So the displacement that goes to any analytical component here would be this computed displacement minus the error, which is defined with this term. And so to start with doing this, we started with MATLAB, the real simple code for the numerical integration of a linear single degree of freedom system with explicit numeric integration. And here's the code, and we are basically having this delay in this line. So this is the computed displacement here, and we have this error term, and we get the displacement with error. And then this displacement is used to compute the restoring force. In this case, it's simple because it's linear elastic, so it's k times u. But we have k times the displacement with error to compute the force. So this is the same thing where you have a specimen and you impose to the specimen an incorrect displacement. So this is simulating that in the analytical domain. So and then with this explicit numeric integration, we can run time series analysis for different periods, right? And then we can run analysis with different delay cases and without delay. And we can compare the two cases and get some difference between the two cases, and that will be our error. So I define my error here with the root mean square error here with this equation, where for each time step I subtract the reference solution, which is the solution with no time delay, from the solution with time delay. So and then we get these for all time steps and get squares and add them and divide it by the number of time steps. And to normalize it, we divide it by the median of the reference solution, and this becomes the root mean square error. So, and then I can repeat this for different periods, right? And then eventually this becomes my root mean square error spectrum, because this axis is period and this axis is some computed quantity. And then here I'm doing that exercise for 3 delay cases, 5 millisecond, 3 millisecond, and 1 millisecond. And obviously for each period, the error for larger delay is larger, which is expected. And as we have seen in the previous presentations, the large period systems are affected less from the delay. As you can see here, when the period increases, the effect of the delay decreases. So this is the investigation in MATLAB for a simple case, but eventually, and this is a simple single degree of freedom elastic case, but we would like to make this investigation for general cases of multi-degree of freedom systems with inelastic response. And to do that, the best way is to implement that in a structural analysis software such as OpenSees, so that we can simulate this condition with errors for multi-degree of freedom systems with delay. And then that has been done with the help of a summer intern. We introduced time delay in OpenSees for several elements, including a zero-length element and a force-based beam column element. And this is the related code for the zero-length element. It's the same thing as in the MATLAB code. We basically have this area term, and this displacement gets used for computation of the resisting force later on. So, and this has been implemented, but we didn't do too many analyses with OpenSees yet, so we'll do those later. Currently, what I will show for the results is just for MATLAB. And then for this implementation, we verified this by comparing with the simple MATLAB case. So this was related to the first subject that I wanted to talk about. The second one is the TVC implementation for improved control in real-time hybrid simulation shaking table testing. This is an exercise we did in building 484 here. So as the background, I have this slide. So for different hybrid simulation categories, we have different accuracy requirements. So for slow testing, we don't need to control velocities or accelerations because they are not important. So we are basically applying the displacements. So the main parameter that needs to be controlled accurately is the displacement. And as we talked today and yesterday, this can be done either by tuning, or you can reduce the velocity and the loading rate to reduce the errors, or in another case, you can do really explicit checking of command and feedback. So you can apply your command until you make sure that the actuator really gets that. So then this would make you be sure that the command is really realized. So in the case of real-time hybrid simulation in an actuator configuration, so this is the real-time hybrid simulation that is done by connecting specimens to the actuator. So it's different than the shaking table configuration. As I mentioned yesterday, the requirement for this is to be able to apply the displacement with the correct rates. Therefore, it's important to control the velocity in addition to the displacement. In this case, the displacement needs to be applied in a certain time. Therefore, we cannot do this explicit checking anymore, but we can still do good tuning to improve the accuracy. And as it has been mentioned many times, the error compensation methods work fine in this case also. For the case of real-time hybrid simulation in a shaking table configuration, in addition to the displacement and velocity, we need the requirement for accurate control of acceleration, because eventually it's a shaking table, right? And the specimen is subject to the acceleration. So accelerations need to be accurately applied to the shaking table and to the specimen. And to do this, the best way is to do this 3-variable control, where you need to control the 3 parameters. And this is basically a slide that shows the need to have the acceleration control, and that shows that displacement control by itself is not sufficient. So this is this 1D platform in building 44 that you have seen in the lab during the lab tour yesterday, and this is ground motion applied to this platform in terms of displacements. And so this is the displacement series. One is command and the other one is feedback. As you can see here, there's a pretty good match. Actually, if I get a zoomed in portion, this match is reasonably good, and we don't have much delay. There is a little bit overshoot, so this is not that important in terms of displacement, but this gets translated to the acceleration as really large errors for lower periods and high frequencies. And the reason for that is the relation between spectral acceleration and spectral displacement, where the spectral acceleration is equal to the frequency squared times the spectral acceleration. So for high frequencies, any error in the displacement gets amplified through the frequency, and we have large error on the spectral acceleration. So basically this shows that controlling only displacement is not sufficient in the case of a real-time hybrid simulation on a shake table, where you need to also control the acceleration accurately. So and then we have also the obvious need for the velocity accurate control. So to be able to do this, the 3-variable control developed by MTS is a well-established displacement, velocity, acceleration control method, and this has already been implemented in the MTS shake table controllers. But for next door in building 484, where we have this MTS 493 controller and the STS software that I mentioned yesterday during the demos, we have a closed loop PID regular control with some feed forward and delta P control capabilities, but this controller particularly does not offer any additional shaking table control features. So we don't have TVC basically in this controller, but it has this pretty nice feature that allows bypassing the controllers by checking this here. So when you do this bypass controllers, the control is passed to an external source, so the control algorithm within the controller is basically bypassed, and you can use any other control algorithm from, let's say, a Selim model to get the voltages, and these voltages directly get sent to the servo valve and transmitted by the controller. So the controller does not run any control algorithm anymore when we have this bypass controllers option. So we control it from outside. And the nice thing about this is when we do this, we still have other useful features of the controller still active. So like the safety features, the yellow button and the interlocks and data recorder and the AC/DC conditioners and so on. So and this is the TVC block diagram, and this has been developed by MTS, as I mentioned, by Brett Tohan, and he had also a Simulink model, and he was kind enough to give us the Simulink model. For our hybrid simulation purposes, we modified it a little bit, and this shows the implemented Simulink model in our system. And basically, what this has is it has these here the gains, the proportional gains for the displacement error, velocity error, and acceleration error, plus the feed-forward gains for the displacement, velocity, and acceleration. And there is also I gain, and there is this delta P gain, and plus some notch filters that you can use, and all of these get added to get some valve command. And here to input to these gains is the errors, right? And error is the difference between the command and the feedback. And this error is for the displacement, velocity, and the acceleration. So eventually we need to have the commands for displacement, velocity, and acceleration, and the feedback. And for that, you only have one command, command in terms of one of the parameters. And let's say in hybrid simulation we have the displacement command, computed displacement, and then from this we compute the compute the displacement command as directly equal to the computed displacement, and get the derivative of this to get the velocity command, and to do a second derivative to get the acceleration command. And for the feedback, we use the displacement measurement of the actuator and an accelerometer measurement to obtain the displacement feedback, acceleration feedback, and the velocity feedback. And these, and then through these we get the errors, and the gains are applied on these errors plus the command values. So, and this here, this shows the block diagram of the PID, the algorithm that already exists in the STS controller. And here, as I mentioned, we have the standard PID plus some F gain and a gain for delta P. So when we have this bypass controllers option checked, we eliminate this, and eventually our control algorithm becomes the TVC. So here I'll show a couple of slides related to the implementation. So since this is a control implementation in a physical environment, we followed step-by-step implementation to avoid any unexpected jumps or movements in the actuators, and to avoid any unexpected damage. So then here I'm showing the steps of this step-by-step implementation. And here the first step was basically to construct the Simulink model to hold a single actuator on the lab floor upon hydraulic power. So we don't, when we get the hydraulic power, we don't want the table to jump, right? So this was the first step to have it ready so that we have a smooth start upon the hydraulic power. And to do that, basically, I assign the feedback value of the actuator to the command so that it stays in position when we have the hydraulic power on. And after completing this step, the second step was hold it in position, plus apply a harmonic signal to the actuator and move it successfully with that. And next, I forgot to mention, we didn't start with the table directly, again for safety reasons. We started with a single actuator that was connected to nothing. And after making sure about these steps on this single actuator, then we moved on to the table and started to move it with a harmonic signal. And one critical thing here is the displacement transducer and the accelerometer signs, measurement signs, need to be consistent for this thing to work properly. Otherwise, the servo commands due to these two things will cancel out, and you would have unexpected controller issues. So we made sure about that, and then so the next step was after this harmonic signal to basically do a shaking table test with the ground motion. And this is the Selim model here for that. And yeah, looks complicated, but I will not show all the details. Basically, what we do here is to be able to run this, we need the displacement feedback, acceleration feedback, and the delta P feedback that we use for the gains. So then we get these into our model, and then this command generation is the part where we hold the actuator in position and then start the ground motion signal. So the ground motion is actually here in this box, and then the commands from this ground motion signal basically goes to here to the TVC block. So this is the TVC block here. So the commands, the inputs to this are the command displacement, displacement feedback, acceleration feedback, and delta P feedback. And the box here, 3 variable control box, runs its algorithm that I have shown in the previous slide. So okay, so then here we need the gains, and we can input the gains of the 3 variable controller through a window like this and run it. And after making sure about all these steps, the next one was to implement, actually improve the model to be able to conduct the real-time hybrid simulation with a shaking table. And this is the Selim model. Actually, Andreas showed the existing model that does the predictor corrector yesterday during the demos. So we added the 3 variable control on that Selim model. So again, similar to the case of the ground motion, we need the displacement feedback, acceleration feedback, and the delta P feedback. But here, in addition, we need the force feedback because we are running the hybrid simulation. So we also get force feedback, and so this box is the predictor corrector that does this prediction while waiting and doing the correction when we get the next command. So different than the ground motion case where we have the displacements already ready, we get the displacement commands as outcome of this predictor corrector box. And then they go here to the command generator, and they are offsetted. And then they eventually go to the 3 variable control, all these inputs. And then the 3 variable control is the same as in the previous ground motion case. So then this becomes our Selim model to run a hybrid simulation with the predictor corrector using the 3 variable control. So so this, I have shown this during the control room overview yesterday. So this is the hybrid simulation system that we have over in building 484. Just to quickly go over it one more time. We have the computational platform, OpenSees generally, but it can be anything, plus OpenFresco, and then we have this simulating real-time target machine which runs in real time, and then that communicates with the controller, and the controller talks to any actuator in the lab, and then this goes in this order for displacements and in the reverse order for the forces. So this is the existing hybrid simulation system before any TVC implementation. So what the TVC does here is, as I mentioned, we implement a Selim model that includes the TVC control. So our Selim model in the real-time machine is the model with including the TVC control, and the change here is the controller doesn't control the actuators anymore. It just transmits the servo valve command that we get from the Selim model. So that's the change in the hybrid simulation system. And so in the next slide, I'll show some of the gains here. And one thing that I would like to mention is Tuning for real-time hybrid simulation, tuning of a shaking table for real-time hybrid simulation is a little bit different than conventional shaking table tuning. In the conventional shaking table tuning, basically you have a random function generator, and then with this, while running the random function generator, you try to get a transfer function that is equal to 1. That's for the amplitudes for different frequencies, and you don't really need to worry that much about the delays, because eventually you are applying what you want to apply a bit delayed, so that doesn't matter in the case of a shaking table. But obviously delay is important for the case of real-time hybrid simulation. Therefore we need to consider gains that would eliminate the delay. So in my particular case here, the gains on the acceleration and velocity feed forward were useful to eliminate the time delay, but this doesn't necessarily mean that these numbers are written in stone or it would work like this in all the cases. It's dependent on other situations and the table itself. And here also what I would like to mention is there was some overshoot due to these velocity and acceleration gains, and this was basically reduced by using some jerk, which is the third derivative of displacement gain. And also the delta P gain was particularly useful to eliminate the oil column frequency, which was actually kind of a headache over in that table. But the delta P was pretty useful to eliminate that problem. Okay, so here I will show the improvement when we have the TVC in terms of acceleration tracking. So I have shown this. This is the response spectrum of the target accelerations and response spectrum of the measured accelerations when we have only displacement control. So when we run the TVC, we see that the response spectrum of the measured accelerations improve, and they get much closer to the target. And specifically in this range, they are matching almost perfectly, and the transfer function is 1, is equal to 1. That is the tracking in terms of accelerations. And for the displacement, so this is the tracking with only displacement control, where you see this slight overshoot, which was the trouble for the acceleration. And for the case of TVC, we still were able to keep the case without the time delay and reduce this overshoot. And after having this implementation, basically we wanted to validation application, and we used this disconnect switch that Professor Selim showed yesterday. And basically what we did is we had an analytical substructure where we modeled the support structure plus most of the insulators, and then tested only one of the insulators on our platform that is independent of all the others. So this was our hybrid simulation setting. And there are some other features in the hybrid simulation, and one is, I mentioned this, you need to use a hybrid simulation compatible integrator, and in this case it needs to be real-time hybrid simulation compatible, therefore it needs to be an efficient algorithm, so we use this alpha operator splitting. And as Andreas mentioned, you need to apply the total accelerations and displacements to the table, and to do that we use the multi-support ground motion. And one thing is we have a three-dimensional analytical substructure, and therefore we have 6 degrees of freedom per node. So our total number of degrees of freedom is this, 200 something, but the bandwidth of the stiffness matrix is large, because we have 6 degrees of freedom per node. So when we get the bandwidth of the stiffness matrix for a 2D system with same number of degrees of freedom, basically it is much smaller because the number of degrees of freedom per node is 3, so that when you get the stiffness matrix, the numbers don't get, the stiffness coefficients don't get apart from each other that much. So why is this important? Because during the numerical integration, at some point we need to solve this linear system of equations, and the number of operations that are required to solve this linear system of equations is equal to proportional to nb squared. N is the number of degrees of freedom and b is the bandwidth. So when your b increases, your computation time increases by this with the square of that. So to basically be able to handle the situation, we use this system solver that does the factorization of the coefficient matrix only once at the beginning of the simulation. And as I mentioned yesterday, we can do that with the alpha operator splitting integration method, because the coefficient matrix is constant during the simulation, it doesn't change. So that's why we were able to use that. And so this basically is a slide that shows the reduction of the computation time with the inclusion of this solver that does the factorization only once. So basically we reduce the computation duration to 1/3 with this solver. And so this slide basically shows the displacement, computed displacement from the hybrid simulation, and I'm just showing the tracking here. We see that the tracking with the TVC is pretty good from the real-time hybrid simulation, and also in terms of acceleration, there's a reasonably good tracking. And then we moved on to using this in real cases to do research, and then also Professor Selim showed this yesterday. So we used this TVC implemented controller for real-time hybrid simulation of electrical equipment that are connected to each other in substations. And to be able to do that, we wanted to basically evaluate two components that are connected to each other with cable. Therefore, we needed two tables for each structure, and one is this that you have seen. And at that time, this was built in-house, and Shaksat helped a lot here in doing this. And once we assembled this table in the lab, both of these were basically tuned with TVC, and this actually required a bit of improvement of the Simulink model, because the Simulink model obviously became a bit more complicated, and the reason is we basically needed two TVC blocks, one for each table. So then, but eventually with this Simulink model, we were able to run a real-time hybrid simulation with two tables using the TVC. And this is just the windows that we input the gains for both tables. And here, what we do in this setting is, as I mentioned, we have two interconnected equipment, and for each of them we model the support structures underneath the tables in the computer, and we test only the equipment that are connected to each other with this cable. So this is our experimental substructure, and we have the support structures as the analytical structures here. And compared to the previous case that I've shown, which had the 3D analytical substructure to do the parametric study faster, we just had a spring mass damper system to represent the support structures for this case. And then, as Andreas mentioned, this becomes really convenient to do parametric studies because you can easily change the support structure condition and run it and finish the whole thing in one day or in one afternoon or one night, whatever. So what we did here is 3 sets of runs. So basically we kept the support structure underneath one of the tables constant, and we changed the other support structure frequency. And we repeated this for 3 support structure frequencies of the second table. And then eventually this results in a total of 33 runs, where we had different cases of support structures on each side. And we were able to investigate the dynamic response of the full set of structures. And this, we had many parameters that we investigated, but this is just a sample that shows the maximum strains that we obtained for each support structure frequency here. And these different sets correspond to different frequencies of this support structure. So one is 3, one is 4, and the other one is 10. And here, this blue is the case that correspond to the strains with no cable. So the case where the 2 equipment are not connected to each other. And what we see from here is basically in this range, which is less than 6 Hz of support structure frequency, which are flexible support structures. The testing without the cable basically underestimates the response. And obviously this is not a desired thing because then you are on the unconservative side. And actually this was possible to arrive at this conclusion was possible only with real-time hybrid simulation, because it would be really difficult to find a table that would accommodate 2 electrical equipment with their support structures. And even if we would be able to find that table, it would be actually quite costly and time-consuming to be able to construct 33 support structures. So therefore, real-time hybrid simulation was a great benefit in this case to be able to make this investigation. Yeah, so this is the...
Thank you.